Okay, you're good to go.
Hey, hello everyone, and welcome back to the 14th LISA Symposium. This is the parallel session on extreme mass ratio Inspirals. I'm Jonathan Gehr from the Albert Einstein Institute in Germany, and I will be chairing this session. We have three talks before the break from Gabriele Piovano, Matteo Bonetti, and Xian Chen. We ask that people submit questions via the chat. You can submit questions at any time. If you do want to ask a question verbally, you can, but please raise your hand and we will answer all the questions at the end of each presentation. Those of you who are following through the live stream on YouTube are also welcome to ask questions. Okay, so we'll now move to our first speaker, who is Gabriele Piovano from the University of Rome La Sapienza, and he will be talking about love and emeries in SPA. Gabriele, please take it away.
Okay, perfect. Thanks, Jonathan, for the introduction, and thanks also to the organizer for allowing me to speak today. I'm Gabriele, postdoc in Rome, and today I'm going to present a recent work done in collaboration with with Andrea and Paolo, and it's all about emeries, love numbers, and the stationary phase approximation. First of all, probably it's maybe not necessary, but just to put all of you on the same page, I'm talking about special types of binary called emeries, which are given by the capture of a stellar massive object by a supermassive black hole. And why these binaries are important? Because of some of the primary targets for LISA. The properties of the binaries can be measured with excellent accuracy. And this may allow to do tests on gravity, on the structure of the components of the binary. And one of the effects that may allow us to distinguish, like, for instance, a supermassive black hole to a supermassive exotic compact objects are the tidal deformabilities. Under certain assumption, the response to tidal deformation on an object can be parameterized by what are called tidal lobe numbers. And for a black hole, the lobe numbers are exactly 0. So it's a bit more complicated, but say the tidal lobe numbers are exactly 0, while for exotic compact object may be very tiny, but different from 0. So the question we wanted to answer to this work is, can we measure the tidal lobe number of supermassive exotic object in emeries and say something about its nature, if it's a black hole or not? And in this work, we did a parameter estimation with a Fisher matrix approach using what is called a stationary phase approximation, plus a few tricks to simplify our analysis. So in this talk, I will maybe say something about how to model the spiral. Well, I move on to the parameter estimation done with the Fisher matrix, the stationary phase approximation, and then I will draw some conclusions and future perspective. So, first of all, the two quantities, I don't know if you can see my cursor, but the two quantities that enter in the waveform are what are called the tidal deformabilities, which are lambda1 and lambda2 of the primary, the supermassive object, and the secondary, the smaller object. And you can see that for the primary, the tidal deformability is proportional to the tidal lobe number, while for the secondary, this quantity is suppressed, lambda2 is suppressed by the mass ratio Q. So it's practically impossible to see any effects tidal lobe number to the secondary, but you can see some effects on the primary. And most importantly, these effects enter a leading order in the gravitational wave phase. So it's an adiabatic, it's called adiabatic effects. And we consider in this work circular equatorial orbits, and we include the effects due to the tidal lobe number of the binding energy and the fluxes through Post-Newtonian terms at 6 p.m. order. And for modeling our spiral, we do the following approach. We consider the binding energy of a point particle, including the contribution of a secondary spin, which are given by these terms here, A0 and A1, where sigma is a small quantity suppressed by the mass ratio Q, with chi the spin of a secondary rescaled by the mass of the secondary. And for the fluxes, we consider Tsiolkovsky fluxes given by F linearized in the secondary spin sigma, including the contribution of the tidal lobe number with our post-Newtonian terms. The same also for binding energy. And with this expression for binding energy and the fluxes here, we have this evolution equation for the radial orbits and the gravitational wave phase. With this, equation here, we can now move on to a parameter estimation with the stationary phase approximation. So we, as I mentioned in the beginning, we did an analysis with what is called a Fisher matrix approach. In the high signal-to-noise ratio, your probability distribution can be approximated by a Gaussian distribution, which is given by where the covariance matrix is given by the inverse, what is called the Fisher matrix, which in turn gives by the scalar products of the derivatives of your waveform. Here we have a sum of the two channels of laser, because under certain assumption we can assume that laser is like two different interferometers, and we sum the contribution given by these two channels. And here we consider 12 parameters for circular equatorial orbits with spin aligned or anti-aligned. You consider the masses, the spins of the primary and the secondary, the initial time, the tidal lobe numbers, and then some of the angles. In particular, this is a theta s, phi s, theta chi, phi chi, gives the sky position and the position of the orbital angular momentum of the binary, and then we also consider the distance from the source. One of the problems of this approach is that the Fisher matrices are usually ill-conditioned. If you have a small numerical systematic error in your Fisher, which translates in large error in the covariant matrices. And some of the problem is due to the fact that these derivatives of the waveform are often computed like with the finite difference method. We found a way using the stationary phase approximation and some analytic trick to at least ameliorate the problem that you have in computing the numerical derivatives. So first of all, this is your approximation of the waveform in the frequency domain. You have all of these expressions here with taking into account also the motion on LISA and what's called the antenna pattern function F of the two channels, which are time-dependent quantities, and also the Doppler shifts due to the motion of LISA. What's important here that maybe some of you will recognize this as one of the typical waveforms that they are now in textbook for the chirp of spiral and circular, spiral binaries in circular equatorial orbits, with the important difference that you have this time tilde f, the orbital phase, and this the omega dot frequency here, which are known numerically, non-analytically. Using this expression here for the SPA, we found a way to compute this derivative of your waveform in a what's called semi-analytic fashion. In the way it's as follows. You have the problem as given by, for the computation of the numerical derivatives by these intrinsic parameters here, the masses, the spin, and the tidal lobe number, which appears in an intrinsic way on your parameters here. So for the time tilde here, which is defined in this way here as a solution of the implicit function, we start till here. For the theorem of implicit function, we can define the derivatives in this way, while for the derivatives of the orbital phase and the orbital radius, we can use this expression here, and the evolution of the derivatives of the wave from respect to our parameter alpha can be given by simply this expression here. We also did some checks to compare the stationary phase approximation with what is called the fast Fourier transform of your time domain signal. We first compute the faithfulness between the two signal, and we can see that even for a fast spinning, also another important thing, we consider any spiral deep down to the ISCO of a Kerr primary. And you can see that this faithfulness here is nicely close to 1. The closer this quantity is here to 1, the better, which means that the two waveforms we are comparing are equivalent in a way. We also did a more important check. We compare the standard deviation compute with the fast Fourier transform, the standard deviation compute with the stationary phase approximation with the same analytic derivatives that I showed before, and we see that the standard deviations computed this way are equivalent, say the error on your parameter. I will explain in a moment what I mean for the prior of keywords. This is mean just to say that the two methods, the stationary phase approximation FFT, are equivalent. So, all being said, can we measure now the Taylor number of the primary? The answer is yes. You can measure it with a very great accuracy. This is the log 10 of the errors, and we consider two cases when we impose a prior on without a prior on the spin of the secondary, which has a large error, so this quantity cannot be detected, but it has an impact on the other parameters. We also consider the case in which we impose a Gaussian priors on the secondary, which simply say that the spin assembly is limited between -1 and +1. In any case, this is the error that we have for the Taylor number of the primary for 0.9 and 0.99. Here we are also on the table for the sky localization of the source and the angular momentum. It's just to say that the Taylor number of the primary can be measured with great accuracy, and these have some consequences in the way in which you can probe some microscopic, or if you want, even Planckian corrections at the event horizon. Because for certain class of exotic compact objects, the distance between the event horizon of a Schwarzschild black hole and the surface of an exotic compact object scale in this way here. And so if you have an accuracy of this level to a Taylor number of the primary, you can put some constraints on the distance between your exotic compact object and the surface of what would be a black hole at this level here. Still, you can put like some very nice constraints, even for mildly spinning primary, as you can see here, where you have like plot the error on the Taylor number on the spin of a primary, and this constraint here can be like several order of magnitudes more stringent than what you have in measure of the Taylor number for the first events with the merger of two neutron stars. But there are some caveats that I'll explain like in a moment in the conclusions. So to sum up, we compute the error of a Taylor number of supermassive object with memories with a Fisher matrix approach, and using some the stationary phase approximation, some analytic tricks, let's say. The Taylor number with primary can be saved with very good accuracy. We may distinguish potentially the supermassive black hole in memories from a several class of echoes, but the relation that I showed before is technically valid for a certain class of exotic compact objects, non-spinning, and we neglected also, most importantly, important cell force effects. We consider simple orbits, and also we simply added a positive contribution tidal number at the positive level, assuming that it's still valuing a strong regime. This is not should be a too dramatic approximation, but still an approximation. And I briefly conclude, say that some future work we consider more general orbits, eventually consider if possible other important effects, and maybe test some probable deviation together with the tidal number. But the very last slides, I should upload soon all the code in this GitHub repository. This works as usual the black hole perturbation toolkit, a fantastic toolkit for if you want to do black hole perturbation computation. And if you have any questions later, you can even send me an email at this address here. And thank you for your attention.
Thank you very much, Gabriele, for that nice talk. Are there any questions? Well, I can ask the first one. What would you think the effect of eccentricity will be to improve the strength of the measurement, or will it make it more complicated because it's likely to be degenerate?
Actually, I don't know. I would expect naively that it will deteriorate a bit the strength of the measurement just because you are adding more parameters in your new analysis. So it's usually the more parameters you have, the less accurate you have can measure all of your parameters, especially the one that are dominant. But one should do the analysis to truly know the answer.
So are you planning to extend to eccentric and ultimately generic waveforms when they're available in the BHPT? I mean, do you know how you would add the tidal corrections in that case?
Actually, I don't know exactly. Probably there are in the literature at least some expressions for maybe small eccentricity. I would say some PN expressions with small eccentricity. I didn't check actually. It's what would be a possible extension. Something that I would like to do is try to use the stationary phase approximation and extend it in the form more generic orbits in the same way as has been done in a paper by Scott Hughes and collaborators, and use that use their method with our method to compute the numerical derivatives and apply it to some parameter estimation. That would be interesting, at least for me.
Okay, thanks. There is a question in the chat from Danny Laghi, who's asking what the range of SNRs you analyzed for the MREs. Did you put them at different distances, or were they?
Let me just go. Here we consider as a distance 1 gigaparsec, and we scale all the SNR to an SNR of 30. Okay. But for this, the configuration here, you can have easily like a relatively high SNR, but to be conservative, we will scale to an SNR of 30.
Thanks. Are there any more questions? In that case, thank you again, Gabriele, and we'll move on to our second talk. So the second speaker today is Matteo Bonetti from the University of Milan Bicocca. He's going to be talking about MREs triggered by massive black hole binaries. Please, Matteo, when you're ready, take it away.
Thank you. So, hi everyone, I'm Matteo. I'm postdoc here at the University of Milan Bicocca, and in this talk, I will present our research work about the formation of extreme mass ratio spiral triggered by the presence of a massive black hole binary. This work has been done in collaboration with all the people listed here. And specifically, this was the master project of two master students, Riccardo Colombo and Giovanni Mazzolari, that now has just started the PhD at the University of Bologna. So, what are MRIs? As Gabriel was saying, MRIs are binary systems with extreme, so very small mass ratio, and they are generally formed by compact objects, so black hole generally, but also neutron star and white dwarf for the stellar mass object, of course. And they are very important source of gravitational wave. So the classical example of MRI is a binary system formed by a massive black hole that we can find at the center of galaxies, and a stellar mass black hole that is orbiting nearby. MRI will be primary gravitational wave sources for the LISA sign case, and in fact we expect that many of them will shine in the most sensitive part of LISA, so here in the bucket. And so they will be very important, especially because the extreme mass ratio makes the gravitational wave emission extremely inefficient. And so this means that we can observe a quite long spiral, up to 10 to the 5 orbital cycle of this object. And so if we can track all this long spiral, we can perform extremely precise measurement and infer something about the source of gravitational waves. And so then we can perform tests. For example, we can precisely map the space-time around the massive black hole and maybe find out deviation from the Kerr metric. So we can do GR tests. We can test cosmology, for the luminosity distance and also the redshift of the source. We can also analyze the nearby environment, considering how the stellar mass compact object distribute around the massive black hole. And if we observe a number of MRI, we can also constrain the massive black hole mass function. And so that we have not to rely only on the merger of massive black hole binaries. How do they form? So generally in the galactic center, we have that the density profiles are generally steep, and so we can reach very high densities. And these high densities generally catalyze very strong dynamical interaction that generate a plethora of phenomena, among which we have MRIs. So the standard formation mechanism is the two-body relaxation channel, in which we have a massive black hole that is surrounded by a cusp of stellar mass compact object. And because of the cumulative interaction, the two-body interaction between all the bodies around the massive black hole, at some point, one of them can be deflected on a very low angular momentum orbit. And this compact object can graze the event horizon of the massive black hole and can be captured in a tightly bound orbit that is driven by gravitational waves. So the system decoupled from the environment. There are no more perturbations that can disturb the gravitational wave spiral. And then the MRI can finally merge after some time. Of course, this is not only, this is the standard formation mechanism, but there are other processes that can bring MRIs. So for example, the binary tidal breakup scenario, in which we have a binary of compact objects that, due to the tidal field of the massive black hole, the binary can be separated, and one of the objects can be captured and the other one can be ejected. And finally, we can have another channel in which MRIs can form in the accretion disk of massive black holes. So in this situation, the viscous torque of the gas there can help in driving the migration of the compact object towards the central object. And differently from the other two channels here, we expect that the eccentricity could be much lower, differently from the standard and the tidal breakup scenario, in which the eccentricity can be quite high. And finally, we can have another possibility. So we can have that MRI can be formed due to the perturbation of another massive black hole. So we can think about the formation of massive black hole binary because, as we know, the structure of our universe can form in a hierarchical way. And so this means that during the cosmic history, you can have merger of galaxies. And if every galaxy hosts at least one massive black hole, then we can form massive black hole binary. So they can be there. So here we analyze exactly this process in 3 different steps. So the first step was to infer which can be the dynamical formation of this kind of object in the context in which we simulate this kind of system. The second step has been to infer how many of them can be found in the universe, the cosmological rate. And then the last step is how many of them we can actually observe with LISA. So something slightly similar was considered in the literature, for example, in this paper by William Wegg, but they consider a much more simplified physics, and we found quite some different results from them. And also recently by Nautz and collaborator, who consider a different mass range and a different approach. So this is our initial setup. So we consider a primary massive black hole that is surrounded by a cusp of Emery, so a cusp of compact object that will be Emery hopefully. And then we have a secondary massive black hole here that forms a binary with the primary. So we are in a configuration that is called hierarchical triple. So we have an inner binary formed by the primary massive black hole and the stellar mass compact object, and the outer binary that is there, the massive black hole binary. We evolved the system through the post-Newtonian equation of motion, but we also consider the effect on the environment. So we have a stellar potential around the primary black hole in order to meet the fact that there are other objects around it, even if we are considering single triplets in each simulation. And we are also considering the effect of the stellar average. Because of the interaction we start, the massive black hole binary shrink during time. And so the two massive black holes get closer and closer with time. So we consider 3 different masses for the primary massive black hole and selected them in the region where we expect that they could be hopefully observed by LISA. So these 3 range of masses, 3 values of the masses. We then consider 4 values of the mass ratio from 0.1 up to 0.03, and 2 different values of the initial orbital eccentricity of the massive black hole binary. For each of these 24 combinations, we consider, we run 20,000 simulations for a grand total that you can see here. So we found that Emerys can be generated in essentially 2 different ways. We can have secular interaction because we have at the beginning an hierarchical triple. And then we can have also chaotic interaction. So in the first stage, the main mechanism that can produce Emerys is the Lido-Kozai mechanism, in which if the orbital plane of the 2 binaries, the outer and the inner, are sufficiently misaligned, the 2 binaries can start to exchange angular momentum, and this exchange generates oscillation between the inclination and the eccentricity of the inner binary. In this plot here, you can observe the relative separation, time evolution of the relative separation of each pair of the bodies. In particular, the orange one is the relative separation between the primary massive black hole binary and the stellar object. That when the spread here means that the eccentricity is growing a lot and the pericenter passage is very small. So this means that eccentricity is growing because of the Lido-Kozai oscillation. However, here we have a complication because the massive black hole binary is actually evolving in time. So the binary is getting tighter and tighter. And at some point, the triplet can lose its hierarchy. And in fact, here, towards the end, we can observe that the situation becomes a bit more messy because the chaotic interactions start to play a relevant role with respect to the second one. And what we have found is that when we have a mass ratio that is particularly high, then secular interaction play a dominant role. While for mass ratio that are much smaller for the massive black hole binary, then chaotic interaction dominates. We can infer this by this histogram on the first line, in which we have the histogram of the initial parameters of all the system that you are simulating. So the one in gray. In green, you can observe the distribution of the parameters of the initial parameters that are then identified as Emerys. And as you can see here, there are a strong selection around 90 degrees, where the Lido-Kozai oscillation are maximized. So here, the secular interaction play a dominant role in driving the formation of Emerys. On the contrary, for the low mass ratio case, there is no selection in the orbital inclination. And so this means that chaotic interaction actually play a dominant role. And in fact, what we have found is that low Q, high eccentricity form Emery through chaotic interaction, while high Q, low massive black hole binary eccentricity generally produce Emery mainly because of secular interaction. And except for one case, we always find that by lowering the mass ratio, the number of Emerys generates increase. Essentially because if the perturber is too massive, the perturbation is too strong, and generally the stellar mass Pompadour is the lightest one, gets ejected very quickly because the three-body problem is unstable. And when the mass is so different, the most likely outcome is the ejection of the lighter of the bodies. So we have the number of M reformed. We also know how long it takes to form them. We can estimate which is the rate. And we have found that the rate is generally 10 up to 100 times larger than the standard MR rate from the two-body relaxation channel. But differently from that rate, this is not a steady state rate, but we have a sort of burst MR formation. And this burst is determined by the lifetime of the binary that has a limited lifetime. In fact, the massive black hole binary shrink because of stellar hardening and then because of gravitational wave emission. So at some point, there will be no binary anymore and only a single massive black hole. So here we probed the efficiency of this kind of interaction in forming MRI. The next step is to infer which is the likelihood of having such kind of system in the universe. And to do this, we coupled our results with a cosmological code, that simulates the cosmological formation of structure. In particular, this code is L galaxies, so a semi-analytical model built up on the merger tree of the Millennium 2 simulation, the dark matter Rayleigh simulation. So this code tracks down the formation of galaxies in the past, and the code can populate each galaxy with a massive black hole, and then we can form a massive black hole binary in the cosmic history. And in particular, for this kind of synthetic universe, we found several mergers of massive black hole binary per year that are distributing the redshift, mass, and mass ratio in this way here that you can observe. We can couple for our efficiency of M formation to these rates here, and what we found is this: that for both the initial value of the orbital eccentricity, we found tens of MRs per year from this kind of channel, and they are distributed in this way here according to the redshift, mass, and mass ratio. Of course, the distribution with redshift is very close to the distribution of the massive black hole binary, because our simulation does not depend on the redshift. But there is a clear trend with the mass of the primary of the massive black hole, so an increasing trend of the massive black hole binary. So here we have more MRs than here. So these are all the MRs in our synthetic universe. Of course, in order to say how many of them can be detected, we need to couple this information with the LISA sensitivity. So we consider a waveform model that is quite simple, the one of Barak and Cutler that we have used also in this work here. So a leading order waveform. And we assume that MRs can be detected when they reach the SNR threshold of 20. And what we have found is that assuming a 4-year of LISA mission, that we have also tens of MRs detected. So 10–15% of all MRs in our synthetic universe could be detected by LISA, considering this kind of channel. And this is the distribution of the SNR that we have. And this is also the distribution of the masses of the primary and the redshift that we have found. So essentially, LISA is able to detect MRs around the smallest mass of our sample here, and our redshift that is around 0.5 or so. And this led me to my conclusion. So the formation rate of MRI from the massive black hole binary channel is generally much higher than the standard two-body relaxation channel, but this concentrating in a formation burst of MRI because of the limited lifetime of binaries, massive black hole binaries. The rate that we have found is much higher than what has been found in the literature, probably because of the more sophisticated physics that we have considered here. And we have a sizable number of MRs that could be detected by this kind of channel. And probably we also underestimating these rates because the limited parameter exploration that we have done, because we have surveyed only a few values of all the possible parameters that we have. And in fact, we can foresee some improvement on this work. For example, we can explore definitely a wider parameter space in order to understand how the rates can increase. And then we can also refine the physics that we consider. So we can introduce also the effect of the spins in our code, because of course the formation of memory is a delicate process that consider how the orbit of the stellar mass compact object grazes the event horizon of the massive black hole. And with spin, we know that the size of the horizon can change. We can also introduce in some way the stochastic kicks that memories are subjected when they are orbiting around the massive black hole, so the interaction with the other compact objects that are there, that here we have neglected, but of course during our simulation we have checked that the time scale of the evolution is below the two-body relaxation time scale in order to safely assume that the system is not perturbed. We can introduce also different stellar potential, and we can also improve the semi-analytical code that simulate the evolution of massive black hole binaries. So we can have a much more reliable rates of massive black hole binary. And finally, we can also find out if there are some specific properties or some peculiarity of the memories that can be formed from this channel in order to be distinguished from those that can be formed from other channels. So thanks a lot.
Thank you very much. If anybody would like to ask a question, please raise your hand. So I was going to ask you about that last point, which is on your slide.
Yes.
Are there things that will allow us to distinguish memories formed through this channel from others? At one point you showed that excess of inclinations near polar, but that was dependent on the mass ratio of the MBH.
Yeah, exactly. So what we have found, so of course here we are neglecting spins, so introducing the spins could change. But what we have found is that there is a slightly preferences of memories that are counter, so the memories are counter-rotating. So there is an excess of objects that are counter-rotating with respect, of course. Here, this is a Schwarzschild black hole, so introducing the spin could change a lot, but we have found this. Another possible indication could be the level of the eccentricity that generally for the causality oscillation can be much higher than in the two-body relaxation channel. So maybe if we can observe at the plunge an eccentricity that is, I don't know, above 0.2, maybe this could be a smoking gun for this kind of process. But yeah, this is not something that is completely obvious to me.
Thank you. There's a question in the chat from Vivian Langen, who's asking how you can resolve the small compact object on the Millennium simulation.
No, of course. Okay. So we are not using the Millennium simulation to resolve this kind of system, of course. We are just using the merger tree of the dark matter halos in order to track down the formation of massive black hole binaries. We run then a quite large number of simulations in which we can resolve the dynamics of triplets of massive black hole plus the stellar mass compact object. But we are only using the information from the Millennium just to say how many massive black hole binaries there are in the universe. Just for this.
There was a second part to the question, which was what was the lower mass threshold for the massive black hole binary rate?
Okay, can I go there? So here in this specific model, essentially the lowest mass is around 10 to the 4 or something, yes, and is essentially due to the seeding mechanism. So I would not trust completely this part here because, of course, there are a lot of uncertainties in how massive black hole forms, and so here it's a matter of assumption. Okay, so yeah, different prescription can produce different mass function at the lowest end.
Thanks. We have a question from Christopher Berry. Go ahead, Christopher.
Hi, thanks for the talk, Matteo. I was wondering, you say in your conclusions that one of the things to do is to survey more of parameter space. And I was wondering what the priorities were. Where do you think is most important to extend?
Yeah, so from the rates that we found, it seems that it's still growing around these masses. And so probably it is worth to explore also this range here, even if, of course, if we go up too much in masses, then LISA will lose sensitivity. But still, probably this could be a good idea in which we have to go. And then, of course, we can also refine more our grid, because we consider 3 values of the masses, 4 values of the mass ratio. Then we can consider a much finer grid in order to smooth these curves here that you can see they are quite edgy.
Cool, thanks.
Thank you very much.
Yeah.
One final question from Elena Rossi, just posted in the chat. Can you make an educated guess on the overall systematic uncertainties from model assumptions on your estimated LISA rates?
Yeah, for sure. One of the biggest assumptions is, well, yeah, it's the waveform model that you're using, that we know that, yeah, it's fine, but not the best that you can find. There are much more sophisticated packages nowadays, but yeah, they are a bit more complicated to run. And so at the end, we stick with the most simplistic one. That is the one of Barak and Cutler. Probably using a more sophisticated waveform can change a bit this number. But yeah, we are confident that the bulk of MRIs can be identified, even if we have used this waveform here. Of course, probably the SNR threshold could be a bit higher in order to be sure that we are detecting anomalies. And so this line will shift a bit on this side. And so probably can lower this number here. But maybe if we have underestimated the rates, maybe, and we can run other simulation, we can verify if the rates are intrinsically higher. And so maybe this can compensate everything. Yeah, so it's...
Okay, thank you. We should move on to the next talk. So the final talk before the short break is from Jian Chen from the University of Peking, who will be talking about the distortion of gravitational wave signals by astrophysical environments.
Okay. Good evening, everyone from Beijing. I am Xian. I'm a faculty member at Peking University. Thank the organizers to give me this opportunity to present my work. The title of my talk is Distortion of Gravitational Wave Signals by Astrophysical Environments.
Xian,
so let me,
would it be okay if you switched your video, your camera on?
It's
Please?
already on.
His camera is on.
Oh, sorry.
Okay, I hope everyone
Sorry,
can see
my
me.
apologies.
Don't worry. So let me just remind you first what LIGO Virgo have detected. They have detected almost about 90 binary black hole mergers, which are shown here by these blue dots. Interestingly, even before the mergers, these black holes, many of them are already 3 to 10 times more massive than the stellar mass black holes we know in the Milky Way in X-ray binaries. So this, of course, raised the interesting question about the origin of these very massive objects. And in the literature, there are a lot of formation scenarios suggested. So when my collaborators and I saw these results, we asked us a quite fundamental question. So how is mass measured in the end? Of course, in gravitational wave, you don't directly see the mass. What you see is this wave signal. It can be characterized by a frequency, amplitude, and the time derivative of frequency. It's chirping, the frequency is increasing with time. So you can do a clever combination of frequency and a frequency dot, get rid of the dependence on the separation of the binary, for example, and then you get a chirp mass. So we all know that. And then you can use the third observable, the amplitude, to further infer the distance. And this is how we measure mass and the distance of gravitational wave sources. But the universe is a bit more complicated than that. The universe is expanding, so there's a cosmological redshift. So what redshift does to a signal is that it redshifts the frequency It also redshifts the frequency dot even more because of time dilation effect. In the end, if you wish to combine the observables to infer a mass, you will find that the mass is no longer the intrinsic chirp mass. It's actually bigger than intrinsic mass by this redshift factor. Unless you know the redshift, otherwise you will always get an overestimated chirp mass. So since I'm trained as astronomer, I know at least two other redshifts, Doppler redshift and a gravitational redshift. So the question I asked to myself was, why haven't LIGO Virgo considered systematically these two redshifts if redshift can indeed boost your measurement of the mass? There's of course a reason. In a standard formation channel, these binaries form in star clusters, disks of galaxies, fields. So they're not moving at very large velocities, and they're not residing in a very deep gravitational potential. So people thought these two effects can be safely neglected. But this understanding is incomplete. In the past few years, there have been a lot of works suggesting that in the accretion disks of AGNs, very close to supermassive black holes, you can also form binary black holes. The merger rate is a bit uncertain, as you can see here, but in some models, the rate is comparable to the LIGO Virgo detection rate. So if these binaries form indeed very close to a supermassive black hole, then neither Doppler redshift nor gravitational redshift can be disregarded, right? So you will see that there will be extra contribution in this redshift factor to boost your measured mass and boost your measured distance. So we did a simple calculation back then, just to put a binary close to a supermassive black hole, a curved black hole. So if the gravitational wave from the merging binary come out of the source in the same direction of its orbital velocity, the wave first will be blue shifted. If the wave come out in the opposite direction, the wave will first be red shifted. But these waves all have to climb out of the potential of the supermassive black hole. So in the end, the gravitational redshift will make the distant waves more redshifted than blue shifted. And the magnitude of this redshift can be a factor of 2 to 10 depending on the distance. So the question is, can you really deliver black holes or stellar mass black hole binaries to the last few structural radii of a supermassive black hole? The answer is yes. If you look at the accretion disk, it's not infinitely thin, it's supported by gas pressure. Most of the disks are hotter inside, cooler outside. So there's a pressure gradient pointing outward in the same direction of centrifugal force against the gravity. For this reason, gas in the accretion disk, at least the outer part of the disk, are rotating slower than Keplerian velocity. On the other hand, small bodies embedded in a disk like a black hole will not feel as much the pressure, so they are still rotating at a Keplerian velocity. So you see that black holes are moving faster than the gas. Then black holes will feel effectively friction and they will migrate inward. Then there's no problem for them to migrate to the vicinity of the supermassive black hole. And then the question is kind of a reversed. The real question is, can you stop them, these small black holes, from falling into the central supermassive black hole? Otherwise, they will just fall into the black hole one by one. You never have the chance of forming a binary. The answer is again, yes. Especially when the accretion rate onto the supermassive black hole is very high, then you will have an inner part of the disk. You can see that this is a log in unit of a Schwarzschild radius. So this is inside 10 Schwarzschild radius. There's a region where the gas is actually rotating super Keplerian. This phenomena is known for a while. In the 1970s, people already pointed this out. This is a consequence of a combination of GR and the fast advection of momentum into the central supermassive black hole. So anyway, in this case, this is the equipotential, and this is where the potential is the deepest and also the pressure is the highest. Inward, there's a pressure gradient. It's pointing towards a black hole, okay, in the same direction of gravity against centrifugal force. So in this part of the disk, gas actually are rotating faster than Keplerian velocity. So they are giving angular momentum to the stellar mass black holes here, if they are stellar mass black holes here. On the other hand, the stellar mass black holes orbiting around the supermassive black hole will lose angular momentum due to gravitational wave radiation. So the gain and the loss of angular momentum will balance somewhere, and which has already been pointed out in the 1994 paper. And you can see that no matter where you put the small stellar black hole, they will all migrate to a place almost at the east coast. This is also in unit of the structural radii. Okay, so we adopted this model and we try to predict where this trapping radius is, and this is the result. Just to guide your eye, this is a total mass of the binary stellar mass black hole. So 10 solar mass black hole is here. Say 20 solar mass black hole in total is here. And this is a mass of the supermass black hole, 10 to the 8 solar mass black hole is here. We see that in a large parameter space, there is indeed this trap, and these numbers indicate their radius in unit of the structural radii. Okay, so in general, your black hole had better to be very massive, and the accretion rate, of course, has better to be high, close to the Eddington rate. In other part of the parameter space, you don't have this trap anymore because small black holes will be flushed into the supermassive black hole very quickly. So from this, we can infer that maybe in the most luminous quasars, you will have this kind of a migration trap. Since there's no more migration trap further inside, we call it the last migration trap. And you can do a simple population synthesis model and predict the rate. This is the result. Anyway, this accounts for about 2% of all the LIGO Virgo events. This may seem to be a small number to you, but don't forget, LIGO Virgo have detected almost 100 binary black hole mergers. So maybe a couple of them is coming from this channel. Interestingly, this source, GW 190521, is one of the most massive binary black hole mergers detected so far. 30 days after the gravitational wave event, there's a AGN in the same sky area just flared up. Okay, so that's why people suggest that maybe this AGN flaring is associated with a gravitational wave source. But interestingly, if you look at the gravitational wave luminosity distance measured from the chirp signal, you see that the distance is 4.5 gigaparsec. And the AGN, by measuring the broad line, you can infer that the luminosity distance is 2.2. So there's a factor of 2 difference here. And then many people take this difference as evidence that the gravitational wave is not associated with the AGN. But in our model, this discrepancy is kind of expected. This is caused by Doppler and the gravitational redshift because the merger is close to a supermassive black hole. I think this is very interesting, and in the future, LIGO and Virgo will certainly detect more such events. Can we distinguish such thing? So since this is an Emery session, many of you may have already recognized that this is Emery. Okay, but the small body now is not a single black hole, but a binary stellar mass black hole. Modeling such a system, especially its dynamics, is very complicated. Each of the black hole is moving very fast around the supermassive black hole. Don't forget, we are dealing with a system at a few gravitational radii. So the velocity around the supermassive black hole is close to the speed of light. So post-Newtonian formalism will certainly break down here. Full numerical relativity is also formidable because if you compare the size of the binary and the background curvature radius, you will see the dynamical range is too large, million to 10 million. So it's very difficult to directly simulate this system. However, we can take advantage of the free fall, the idea of free fall. So if you stay in the free fall frame, since we want to use LISA to track this binary, so this binary is maybe a month to years before the merger. If you stay in the free fall frame, at that stage, the two black holes are not moving extremely fast relative to each other. Their velocity is mildly relativistic or even Keplerian. So we can model the binary motion in the free fall frame very well. On the other hand, the binary at this stage is very small compared to the background curvature, which means if you stay in the free fall frame, the space-time is effectively very flat. There's only small perturbation induced by the existence of the supermassive black hole here. But that small perturbation can be treated as a perturbation to the equation motion, which effectively produces this so-called gravito-electromagnetic forces, which can be easily inserted into the equation motion and study the evolution. So the trick is simulate the system in a free fall frame, and this is the result. So without the black hole, of course, the binary will just move on concentric circles like the blue and the orange circles, and they will not move. But because there's a nearby supermassive black hole here, it induces this like electric or magnetic-like forces as is indicated by these arrows and colors. then the binary will start to drift relative to the free-fall frame. Now, the black line here is showing you the center of mass. You will see that in the radial direction, there's an oscillation, and in the azimuthal direction, relative to supermassive black hole, there's a drift. Okay. This is a motion relative to the free-fall frame, which means the binary, at least the center of mass, is not following a geodesic. It actually deviates from the geodesic. And don't forget that we put the binary at 3.3 gravitational radii. It's very, very close to the central supermassive black hole. If you put the binary even closer at 2.8 gravitational radii, then the evolution is more irregular. This is closely linked to the fact that the inner binary will soon become very eccentric. The eccentricity is excited by basically a combination of the tidal force and also the gravito-electromagnetic forces. At this large eccentricity, the binary will certainly merge. Here, the binary didn't merge because we haven't put in the PN terms yet. But if you put the PN term, then in many cases, these binaries will merge. Then this produces an interesting coincidence between smaller distance to the black hole and the binary black hole merger. This is a coincidence that we are looking for at the beginning of the talk, right? This will be the redshifted source. And I already mentioned that the center of mass deviates from a geodesic. And in several hours, it deviates this amount, but in 8 days, it will deviate already by 1 radian. So if you are treating the binary as test particle, then you will be certainly wrong in 8 days. So I think by looking for this deviation, you can also infer whether or not the small body in the emery is a single body or a binary. If the binary merges, then the gravitational radiation will take away momentum and cause the merged product to recoil. And this will induce a kick on the merged product. This will produce an interesting glitch in the orbit around the supermassive black hole. And this is also a glitch in the emery waveform. Don't forget the orbital motion around the supermassive black hole produces low frequency waves that is basically an emery waveform. So this blue curve is the waveform without a kick. Red is where we introduce a kick at time 0. And after about half a day, you can already see by eye that the kick will induce perceivable differences. So this half day is also kind of a time resolution. You need to wait this amount of time to see the difference. Then you can use this difference to infer interesting things like the recoil velocity of the merged product. And look at the accuracy here. Here we induce only a very small recoil velocity, 10 kilometers per second, which is certainly much smaller than what will happen in the real universe. And you can reach an accuracy of 1% to measure this recoil velocity. You can also measure how much mass is taken away by the merger of the 2 black holes. Gravitational radiation takes away rest mass, and the accuracy can be 2%. The point is that these constraints are 10 times better than the current constraint put by LIGO-Virgo by measuring the merger Rindown waveform, for example. Another interesting test of fundamental physics is test of the dispersion relation.
You've got 2 minutes left, please.
Sure, I'm almost done. Okay. So the merger of the binary produces high frequency wave, and its orbit around the supermassive black hole produces low frequency wave. In some massive graviton models, these waves are traveling at different times. So you can look at the arrival time of the merger signal, like a LIGO-Virgo signal or a glitch in the emery, and look for this time delay. Say if you don't see delay, then it means that the delay is smaller than half a day, the resolution I talked about in the last slide. And you can use this to constrain the mass of the graviton. For example, in this case, you can constrain the Compton wavelengths of your graviton to this level. Compared to the constraint currently done by LIGO-Virgo, using this kind of binary emery, you can achieve a 10 times better constraint on the graviton mass. So a short conclusion, I wanted to say this source is interesting, but now I realize it's also a mess because the dynamics is very rich. So it also indicates that the waveform is extremely complicated to model. I do think some model independent algorithm is needed to extract this signal finally out of the LISA data stream. Thank you all.
Thank you very much. If anybody has questions, please raise your hand. I see there is one from Christian. Please go ahead.
Hi, thanks. That was a very interesting talk. So I had a question about the fact that you said that you could determine the by looking at the dephasing. In 8 days, that you could tell if it was a binary. So I'm always wary with these arguments because there are many different sources of dephasing. So I was wondering if there's anything specific to this situation where you would know that this dephasing is to do with it being a binary, or if this is going to be degenerate with other astrophysics.
Right. Of course, this is still a working in progress. We're trying to find the distinctive signature, but I want to point out there are two kinds of dephasing. One is due to the kick and the recoil. You see the dephasing here by eye. Another dephasing is here. This is due to the fact that you have some internal structure of your small body that also introduces a dephasing. Whether this will degenerate with some other effects, for example, nearby gas or some dark matter cusps or something, we are working on it. So I would not say, I don't have a conclusion yet, let's say. I think in some parameter space, we do think we can distinguish these or did sort of break the degeneracies, but there are cases we do see a very strong degeneracy.
Okay, thanks.
I don't see any more questions from the room for the moment, but can you say a bit more about GW 1905-21? You said that the factor of 2 distance discrepancy could be explained by these effects. If you assume that this is the explanation, how close was the object to the central black hole?
So this is a factor of 2. If the central black hole is a Schwarzschild, it's at the ESCO. If the central supermassive black hole is a curl, then it's even further away from the ESCO. It doesn't have to be that extreme. Like 2 times the ESCO is already fine.
I see. Okay. And in the binary Emery case, if we assume that LISA is operating concurrently with 3G detectors, presumably the gravitational waves in the binary would themselves be detectable by ground-based detectors. So this is a potential multi-band source.
Yes, indeed. It's a multi-band really at the same time. You see them at not like wait 3 months to see the event turning up in no, you see them at the same time. I see that Stas has a raised hand.
Yeah, go ahead, Stas.
Excellent. I have a question about exactly on this. It's about last migration trap. So as far as I know, last migration trap is usually a few hundred Schwarzschild radio, gravitational radii, and you are talking about really close to the last stable orbit. How do you bring it from the trap where you want them to kind of form to the very end?
It's a different mechanism. So the usual migration trap you see is basically somewhere here due to the discontinuities in the accretion disk. But our migration trap is caused by first fast accretion, and then you have this super Keplerian rotating region. And this will give angular momentum to stellar mass black holes. And the loss of momentum due to gravitational wave radiation will keep the balance in the end. Well, you can look into more detail in this paper.
Okay,
the final trap is. So it's different from the standard migration trap.
Okay, thank you very much. I don't see any more questions, so we'll move to our short break. We're slightly over time, not very much. So we'll come back at 4:20 and have the last 3 talks then. Thanks to all of our speakers from this first part of the session.
Hello.
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 Hello. Yeah, I think I had the wrong link for the I ended up in the wrong room.
Okay, that's
Is
great.
this
Good. Good.
the
You've made it
Emory
now.
one?
That's
Yeah,
correct.
sorry about that. I'm not sure what happened.
Not at all. We'll get started in a few minutes. We're waiting for John to return from his break too.
Okay, so maybe he's gone into the wrong, possibly into the wrong one as well, or?
No, he was here previously. We're
Okay.
just he
Okay.
just switched, jumped out.
Okay, that's fine. Yeah.
Actually, perhaps I should offer, would any of the three presenters wish to practice or bring up their slides before we get started? If not, we'll get going when John arrives.
Yeah, I'm first, so I guess I can just check mine's working.
Okay. Perfect. Let's your desktop.
A preview of the end, I think that's
Yep, that's looking good.
great. Thanks.
Am I okay to quickly test as well?
Yeah, please do.
Okay, so you can see a screen
Desktop, yeah.
and a slide, yeah?
Yeah, perfect.
Okay, great. Thank you.
You're muted, Leo. Yeah, we can see your presentation. Perfect.
Okay. Sorry, I couldn't figure out how to stop sharing.
Okay, I see Jonathan has rejoined us, so I'm going to mute myself. Pass over to him.
Thank you very much. Welcome back, everybody, to the second half of the Emory parallel session. We have three more presentations in this half, the first of which will be given by Barry Wardell from University College Dublin on gravitational waveforms for compact binaries from second-order self-force theory. Begin when you're ready, Barry.
Thanks very much. I'll just share my screen. Hopefully everyone can see that.
Yep.
Great. Yeah, so I'm going to talk a little bit about some recent results we have for producing waveforms for extreme mass ratio inspirals using an approach called the second order self-force theory. this has been an ongoing collaboration with a number of people, including those listed at the bottom here, and also some others who've joined since some of this earlier work. You can find the results from this talk, particularly in the last of these archive links, but also some of the earlier ones have some of the preliminary work we did to build towards it. So just before I get on to results, it's worth thinking about, first off, why are we using cell-force theory as a way to produce waveforms? Well, I think we're all here familiar with these sorts of characteristic strain curves for least emission. And the thing that I'm really interested in are these Emery harmonics that appear kind of down here towards the bottom, these dark red streaks. And these represent signals from extreme mass ratio inspirals. And they're a very prominent source for the least emission. And LISA is going to be able to both detect and estimate parameters for these things with a very, very high degree of accuracy. So what is an extreme mass ratio inspiral? In the session, I probably don't need to spend long on this, but suffice to say, they're binary black hole systems with a very large mass ratio, 10 to the 6 or so. They'll undergo a large number of orbits during the life of the least emission. And we need to be able to produce waveforms that are very accurate to better than 1 radian over the entire inspiral. So that's the LISA motivation, which I'm sure people here are already familiar with. There is another motivation we had for doing these this cell-force theory approach to waveforms, and that's more immediate. If we look at the systems that LIGO has detected up to recently, there's quite a lot of them now, but there's one particularly interesting one for people like myself working in cell-force theory, and that's this one. This particular system, I just moved the zoom thing out of my way, was the GW191219 observation, and the important property it has is that it has quite a large mass ratio, the largest one we've seen so far, so about 26 to 1 or so, and that's starting to get into the regime of where cell-force theory actually becomes a viable and valid way to produce waveforms. So that's the motivation. How do we go about actually doing this? So the how of cell-force, I'm going to keep this fairly short because I could spend a long time getting into a lot of technical details. Really, to summarize, what we want to do is we want to figure out how to model a binary system with 2 black holes, a big one, M1, and a small one, M2, and the gravitational waves that come off of it. And these could be spinning, and they may not be in simple circular orbits. The way we do that is by solving Einstein's equation. Now, it's very hard to solve Einstein's equation exactly in this case. So what we do is we think about a series expansion in a small parameter. And luckily for us, we do have a small parameter, the ratio of the mass of the small black hole to the mass of the big black hole. And we're going to take this expansion, in fact, to quadratic order in the series expansion. At the 0th order, all you have is the big black hole on its own. That's going to be a Schwarzschild or a Kerr black hole. But if you then substitute this expansion into Einstein's equations and expand out order by order using normal perturbation theory methods, you get a sequence of equations. The first one at epsilon to 0 is just tells you that the big black hole is the solution of Einstein's equation. At epsilon to 1, you get an equation here for H1, and at epsilon 2, you get an equation for H2. And the right-hand side of these guys involves some technical things, these H1S's. I don't want to get into that, but at 2nd order, you also have the quadratic in H1 pieces feeding into as a source for the 2nd order field equations. There's a slight extra technicality to what we do in that we also perform a 2 timescale expansion. So the orbit is evolving slowly, but the black hole is going around on a relatively fast timescale relative to that in-spiral timescale. So it's actually a good idea to do a 2 timescale expansion of these equations to separate out those 2 scales. And there's a lot of detail in this slide, but what I really want to highlight is the hard part. And the hard part is computing this source for the 2nd order Einstein equation. There's a huge amount of work that goes into this. And that's really the big challenge, getting this computed accurately. Okay, but what we spent the last number of years doing is actually setting up these equations and solving for H1 and H2. And then the question is, how do we then turn that into a waveform? Well, there are 2 parts. First off, if we look in the middle here, what we want to do is solve for the orbit of the small black hole around the big black hole. And in the quasi-circular case, where you just have circular orbits, you just have an orbital frequency that evolves over time slowly due to forcing terms. And these forcing terms are actually functions of these H1s and H2s that we've computed. Once you have the frequency, then the orbital phase is just an integral of the frequency. And so that's how we solve for the orbit. We then think about how we want to compute the waveform. Well, if you think about the waveform, we can factor it in this form here, where it's the strain as a function of time is a sum of our modes of an amplitude times e to the im phi p, where phi p is the orbital phase, not necessarily the gravitational wave phase. So these are also complex. And these a's are the thing that we actually need to compute. The way we do that is by writing them in terms of H1 and H2. And in fact, they are just the mass ratio times H1 plus the mass ratio squared times H2. So our basic algorithm here is that we pre-compute H1 and H2 on a grid of points. That's a slow process, but we only do it once by solving the Einstein equations. And then once we've built up that data, we can then actually generate new waveforms for any mass ratio in essentially milliseconds by solving this ODE here. So it's actually a very efficient approach once you've done the hard work up front of pre-computing these H1s and H2s as a function of frequency. So there's one other slight shortcut we've taken in the current approach we do. So these F1s and F2s, these are forcing terms. Strictly speaking, the way you compute these is by working out what H1 is at the location of the small black hole and feeding it into a formula. We've actually done something slightly different, and which introduces a small approximation, and that's to use a flux balance law to actually compute something slightly easier than these two things, and use that instead. So the basic idea is we say that the flux of radiation to infinity is the rate of change of the bonding mass, and the bonding mass can be written in terms of the masses of the two black holes and the binding energy of the system. We can then start to ignore things. The change in the mass of the small black hole is a higher order in mass ratio effect, so we can ignore that straight away. We can then use the chain rule to take the derivative of the binding energy with respect to time and write it as derivative with respect to the parameters, the frequencies and the masses. And then we can make another approximation, which isn't higher order in the mass ratio, but is justified by the fact that these two terms are actually small. The mass of the big black hole and the spin are not evolving very much over the inspiral. So we can actually ignore these two and then just rearrange this equation to find d omega dt. And that's exactly what we do. So instead of solving that d omega dt equals forcing terms, we have a slightly different equation we solve where d omega dt is the ratio between the flux and derivative of the binding energy with respect to frequency. And these two things are actually functions of H1 and H2, so they reappear in here, but in a slightly simpler form than before. Okay, so that's it for the method. Let's get on to some results. So the waveforms, when you run this whole through, what you find is something that looks a bit like this. So we've only done quasi-circular inspirals so far in Schwarzschild case. So you can see the inspiral here starts slowly, and gradually as the two black holes get closer, the inspiral gets faster. That's kind of makes intuitive sense. And down at the bottom, you have a waveform which oscillates basically with twice the orbital frequency, but gets larger in amplitude as time goes by, and also higher frequency. That's a very qualitative picture. We can actually be a bit more quantitative about this and do some comparisons with known results. So in particular, numerical relativity has produced some very nice simulations involving not necessarily extreme mass ratio inspirals, but systems that have mass ratio of 1 to 10, which is starting to get to where you might expect perturbation theory to have some validity, if not being perfect. So we've done that. We've taken a numerical relativity simulation from the SXS collaboration, which is shown here in the black. This is the real part of the 2-2 mode. And you can see the simulation started here with some junk radiation and then inspiraled, and then there's a merger over here on the right, and then the ring then. And superimposed on top of the black one, which is numerical relativity, the exact reference result we're trying to get to, we have the orange one, And the orange one is what you get from second order self-force theory. So from all those calculations I talked about. And you can see that they stay very well in phase, and amplitude also looks pretty good, right way up until pretty close to merger. I'll come back to that in a minute. Just to give you an idea of how important it is to include that second order metric perturbation, H2. If you don't, you get this blue curve here, which I just zoomed in on the last phase. And you can see the blue one is completely out of phase with the other two, despite the orange and the black being on top of each other. So it really is crucial in order to maintain phase coherence through the Inspiral that you have the second order piece. This is for Q10, which you already might think is pushing it a little bit if you talk about an expansion in 1/Q. But it turns out that actually if you go all the way to Q1, which seems like it's got no hope of working, you're doing a perturbative expansion in a parameter which is order 1. In fact, it still does pretty well. It doesn't do perfectly, and you can see that the dephasing here towards the merger is certainly a lot worse than Q10. In fact, we know exactly how the dephasing should scale. It should scale like Q. So this is probably 10 times worse than this one. But it still does a fairly good job, given that this is a waveform that we were able to produce in milliseconds, whereas the numerical relativity simulation might have taken tens of thousands of CPU hours. So moving on just to a few more things, we can also check that the amplitudes agree very well. So this is the magnitude of the waveform amplitude of the 2-2 mode for that Q equals 10 case. And there is a black curve underneath this blue one. They basically are perfect up until the end. And also we can compute higher modes very easily here. So the 3, 3, 4, 4, and 5, 5 modes are also very good. There are some, if you look very closely, you can see some wiggles here. These are actually in the numerical relativity waveform, not in the self-force one. So that's where we got to as of this paper on the bottom here. Since then, since the end of last year, we've been working on improvements. So one improvement we have is to start adding spin. And when I talk about spin here, I mean, first of all, the spin on the smaller black hole is the easier one to add. You can think of that as having a component parallel to the orbital angular momentum and perpendicular. So we can think about those two types of spin, the red one and the blue one. And the perpendicular one obviously changes the orbit as well, makes it kind of bob up and down. But we can add this quite easily, and this was described in a paper here by Josh Matthews. So you can see some of the results in there. I'm just going to show the results of that paper, the waveforms you get. So for example, here we have, if you have the secondary spin, and so this is a case where you have mass ratio 6, secondary black hole, the smaller black hole has a spin of -0.8, so it's quite large. You can see if you don't include the effect of the secondary spin, you get this blue curve and the dephasing gets pretty bad towards the end. If you do include the effect of the secondary spin, you get the orange one, and you can see that it's tracking pretty close to the NR one. It's not perfect, but it's pretty good. So certainly we're getting the secondary spin right. We can also include spin on the bigger black hole, the primary, as long as it's small. So here's an example showing that, where mass ratio 8, you still have a spin on the secondary black hole, which is 0.8, but we also have a small spin on the primary. And you can see if you don't include those two spins, you get the blue one, which again is pretty far off the black one towards merger, whereas the orange stays pretty close. And then the last thing we can do is we can also add that processing spin. And here's an example for that, which is somewhat preliminary, but has added processing spin. Okay, I think I'm coming up towards the end here, so let me just mention one or two other things. Another improvement we have is adding a model for the transition and plunge part of the waveform. So if we look back at this waveform that I showed over on the right here towards merger, you can see that something is going wrong. So if we zoom into that region, there is a dephasing happening here. So the orange is dephasing from the black, but also the orange one just completely stops. And the reason for this is that our whole model based on a 2 timescale framework breaks down. Our 2 timescale model assumes that the orbit is evolving slowly, whereas you can see as the orbit spirals inwards, it starts to spiral in faster and faster. And eventually it's no longer evolving adiabatically, and that whole approximation doesn't really hold. But the good news is we can switch to a different model at that point and produce a composite model that does work. So to show some preliminary results for this, back to our 2 waveforms, I'm going to mark on here where I think our current model is breaking down or starting to break down. So the orbit is starting to cease to be adiabatically evolving. And then what we'll do is we'll zoom in and just on the region after that point here. So you can see this is the plot I showed before. And you can see we stop at this gray point where the model completely fails. If we then substitute instead of that model a transition approximation, so transition expansion, at leading order in the transition approximation, we get this red one. You can see it goes right through, although it starts to dephase. But once we start to add just the first subleading effect, we're starting to do pretty well, almost right up to merger. And we actually plan to add about 8 orders in here. So we're hoping that this will really do a very good job right away up, pretty close until merger. Okay, so I think I'm pretty much at the 15-minute mark there. So let me just wrap up with some conclusions. We can produce waveforms in the quasi-circular case, non-spinning, but also starting to add spin for arbitrary mass ratios. And they're very fast to produce. We can do these things in milliseconds. For the complete waveform, we need to add on something to deal with the transition, plunge, merger, and ring down. We've done some very detailed comparisons with numerical relativity, post-Newtonian and EOB, and shown very good agreement, and actually also started to quantify the disagreement. It's possible that this could also be suitable for LIGO, in addition to being really a great way to do least Emery's. And it's relatively easy to add effects in this model. So like non-aligned spin, secondary spin, small eccentricity, things like that are fairly easy. I'll leave up maybe the outlook here just as a final slide. So we have a lot of improvements to make. We have to make our calculation more efficient for a start. So that's using things like costly formalism. We could figure out, are there hard things to compute that can be left out in practice? We really need to go to having the bigger black hole being a generic curve black hole. So that's really the big challenge. And incorporating other finite size effects is also an interesting thing to do. So let me leave it there, and thank you for your time.
Thank you very much, Barry. I see Christian has raised a hand. If anybody else would like to ask questions, please put your hand up. I will go through them one at a time. Christian, go ahead.
Hey, thanks. Really interesting talk. Thanks. Really good explanation of some quite complicated stuff. This might be too technical to kind of answer quickly, but if you could roughly summarize what the challenges are in introducing higher spins for the primary, that would be interesting, because it seemed like even introducing a spin of 0.1 is quite tough, for example.
Yeah, so spin of 0.1, what we did was we actually expanded the equations in the spin of the big black hole, and then you get Schwarzschild equations again. So the hard part is solving these equations here, where the space-time is Kerr. So doing perturbation theory in Kerr is much harder than doing perturbation theory in Schwarzschild space-time. And we can do linear spin corrections by still working in Schwarzschild space-time. So it's sort of a little cheat, but it's a lot more difficult to solve the Kerr equations than it is the Schwarzschild ones.
Okay, thanks.
Yeah.
There's also a question from Stas. Go ahead, Stas.
Thank you. Hey, Barry, I will cheat. I will ask you 2 questions. The first question is about spin supplementary condition. So when you introduce the spins, you need to do something for self-force, and spin supplementary, and it might not match whatever is spin definitions in numerical relativity. How you deal with that? And my second question, probably easier, is about how sensitive are you to the choosing of alignment point between 2 waveforms?
Right. So the first question, the spins one, we use the Tulchev-Dixon spin supplementary condition. Although we're actually only working to linear by working to linear order in the mass ratio, or to certain order in the mass ratio, that actually means that you don't have to worry about quadratic spin effects on the secondary. So in fact, it's much less sensitive to spin supplementary conditions than the completely generic case where you don't have this perturbation theory expansion. So hopefully that answers that one. So what was the second question?
Alignment, when you align.
Alignment, right, yes. Yeah, so you do have to be careful to align your waveforms correctly. So we set the initial frequencies to match of our waveforms, and then at a point, and then we don't do any further alignment after that. So it's not quite as bad as you would get, for example, in trying to compare against numerical relativity, where the frequency might be oscillating due to gauge effects and things like that. We do have to be careful about that. So it's tricky to get right, but we've been careful about it. There will be a paper about this coming out possibly this week with ourselves and also Angelica Albertini and Alessandro Nagar. So there'll be more details in there about the alignment.
Thank you very much, Murray. I think we should move on to the next talk.
Yep, let me just stop my share here.
Okay, our next speaker is Leo Stein from the University of Mississippi. He'll be talking about tidally induced nonlinear resonances in MREs with an analog model. Please, Leo, when you're ready, please start.
Can you see my screen?
Yes.
Okay, and sorry, the Zoom chat window goes away, so I can't see any questions anymore.
Yeah, we'll save all the questions for the end.
Okay, great. All right.
If you have questions along, please do type in the chat.
All right. All right. So thanks everybody for coming. I'm Leo Stein. This is based on work that's on the archive at this archive number here. And this work was led by a grad student, David Bronicki, who's also at the University of Mississippi, and Alejandro Cardenas Avendaño, who is a postdoc at Princeton. And Alejandro has a newborn and David has like a 1-month-old or something. So that's why I'm here. Anything that I say wrong is my fault, and anything that you think is good about this work is their doing. Okay, so let me just give you the punchline in case you want to go back to checking your email. I think the important thing to remember from our work is the following. So in MREs, very small perturbations are important because they will be very sensitive to lots of physics. One type of perturbation that we know exists out there in the universe that is unavoidable is due to the gravitational effect of everything else in the universe that's nearby that causes a tide on an MRE system. And perturbations are more important when you get to orbital resonances. So at resonances, torus averaging fails. Not that averaging is always the thing to do. But anyway, let's focus on these resonant dynamics. At resonances, we'll break the cam tori of the geodesic orbit system, and that can lead to nonlinear resonances and even to chaos. So resonances are very sensitive to external perturbations. So what we want is a tool to be able to quantify what the effects of nonlinear resonances are going to be and whether or not they're important. Should we be modeling them? So rather than doing the harder problem in Kerr, we're starting with a toy model, which is a Newtonian analog to Kerr that shares a lot of its properties. We just studied one particular resonance, the 2 to 3 radial to polar resonance. And the punchline of the type of analysis that we introduced is the following. So at a tidal perturbation, there are now 2 small parameters. We already have the small parameter that's the mass ratio Q. And now we have a new small parameter epsilon that measures the strength of the tide. So if it was due to some third body that's nearby of mass m star at a distance d, then you would get some non-dimensional epsilon on the right-hand side here. And so what's important is a ratio between 2 small quantities. And we found the following scaling, which is something that's predicted by general principles. So when q squared times some coefficient c is less than approximately epsilon, then you must model the tide, or else you will get the model wrong, or else you'll get the motion of the body wrong and the gravitational waves wrong. And this parameter c is approximately 300 we found for the one resonance that we looked at. Okay, so let me get now into the details. So MREs are going to be precision probes of strong field gravity. And they're going to, even though their gravitational waves might be very small, they're very far away, and the small body is not that massive. There's still going to be a very large number of cycles, 10 to the 4 to 10 to the 5 cycles, and signal noise ratio might be up to 1,000 optimistically. And there are lots of small effects to take into consideration. Barry was already talking about some of them. Question is, where should we be focusing our efforts? So that's why we're doing this toy model problem instead of just diving into the hard problem. So there are lots of possible external tidal perturbations. You could have a third body. You could have the potential of the whole galaxy that you're embedded in. There could be some dark matter spike around the supermassive black hole. And we're going to focus on resonances. That's what's kind of generally predicted from perturbations of integrable systems. Away from resonances, perturbations are not as important. Okay, so what we want to see is the nonlinear effect. So we're going to integrate the tidally perturbed dynamics, and then we're going to study the gravitational waves with the kludge model. So the toy model that we're using here goes back to the 18th century. This is the Euler two-fixed center potential. You just take two masses of two different masses, fix them in space, and then you have some test body that moves in that background potential, and that turns out to be integrable. So there's the energy, and there's the axisymmetry about that line connecting the two bodies, and there's some third quantity that's kind of like the Carter constant that's not due to an isometry. Now, if you take these two masses and make them the same and make a purely imaginary separation between the two of them, then you get a real oblate potential. So that's kind of like the Kerr geometry. And you can separate it in oblate spheroidal coordinates and switch to something like action angle variables and switch to amino-like time. And you get these equations for the trajectory. So if you're familiar with orbits in Kerr, then this should look pretty familiar. These are polynomials. Okay, and so what about adding a tidal perturbation? In GR, you would have some asymptotic value for the tidal tensor. And you can do the full thing in GR by finding a Hertz potential and then doing metric reconstruction. Then you would have a metric, and you would evolve an orbit in that perturbed metric. But we're not doing that. We're just doing the easy thing. So the Newtonian case, you would expand the potential of the external universe around the origin of coordinates. This constant doesn't matter. You go to the freely falling frame, so there's no linear bit, and then you just have a quadratic bit in separations. And so if you rescale everything, then all of the smallness is in this epsilon, which for a third body goes like this: m squared m star over d cubed. Okay, so that's the potential that we're adding to our Hamiltonian. We're not including radiation reaction in this analysis. We're just doing the Hamiltonian treatment. And so, adding radiation reaction is very important, but we're not doing that quite yet. And so we want to involve the full dynamics. We don't want to do some approximate treatment by averaging. And so we want to involve for many cycles, so we need to be phase accurate. So we use a symplectic splitting integrator. So split the Hamiltonian into two pieces, H0 and H1, which are each separately easy to integrate for a long time, or for a long time accurately. And so this is the infinitesimal flow generator. And if you exponentiate it, then you use Baker-Campbell-Hausdorff to split it. And so you interleave integrating with switching back and forth between these H0 and H1, weighted by these parameters A1, B1, A2, B2, and so on. And so for us, H0 is the background integrable dynamics where we have analytic solutions. And our H1 is just a purely spatial perturbation, so it's just a momentum kick. So that's also easy to integrate. Okay, let's skip this. So what happens at resonance? So in general, we have an integrable system. So phase space is foliated by tori, and on a general torus, like this green one, you would have motion that kind of fills the torus. So there's no special direction. But on a resonant torus, the motion is going to recur periodically. And now there's going to be some special direction, because this figure of the orbit does not sweep through the whole torus. It just keeps going around the same point. So your initial phase where you are around the torus is very important. So for example, if you had a tidal perturber at a particular direction in space, then on a resonant orbit, your orbital shape could actually be aligned or misaligned relative to that perturbation. So effects will build up instead of averaging out. Okay, so you can see these effects on Poincare surfaces of section. That's a convenient way to spot what's happening. So if it was a purely integrable system, then your surfaces of section would just be a bunch of nested tori. But then what happens at a resonance is a resonant torus would have a bunch of fixed points around it, alternating between elliptic and hyperbolic. And once you crank up the perturbation, then your resonant torus is going to break into a chain of islands. And you're going to have kind of circulation around these elliptic fixed points within these little new broken tori. And outside, you'll have oscillations inside here, and you'll have circulation out here in a boundary layer around there. And you could have a very thin chaotic region around here. Okay, good. So we actually have a 6-dimensional phase space, which means when we make a Poincare section, it'll be a 4-dimensional figure, which is hard to visualize. So here's what it looks like for our system. We've got 3 directions and 1 color for the 4 dimensions. And this would have been just a single torus if it was one of the non-resonant tori. But this is close to the hyperbolic fixed point of a chain of islands that's on a resonant torus. And so you can see that we're kind of filling out that boundary layer around them. And so it's hard to see in projection, but when you look at the whole 4-dimensional Poincare section, it's clear that you've actually broken the background torus. So a nonlinear resonance is important here. All right, so the other thing that you should do at a resonance is you should define a new dynamical quantity, which is going to have a new time scale in the system. So this new quantity is called a resonance angle. So we're talking about, in our example, a radial polar resonance. So there's some, for the unperturbed system, there's some common frequency, omega naught, and then the other two, the radial and the polar, are multiples of that. So every time the radial oscillations complete 3 radial oscillations, the polar oscillations complete 2. So you can combine psi and chi, the phase parameters, into a new capital psi, 3 chi. So this quantity would be constant for the unperturbed system. But for the perturbed system, there's going to be some variation for this because the resonance dynamics are going to turn this resonance angle into kind of like nonlinear oscillator. And so there's a new time scale for this resonance angle, capital psi, and depending on whether you're inside one of those elliptic islands or in the hyperbolic region outside of that, this variable will either oscillate or it will circulate. And the dynamics of this capital psi depends on the strength of the perturbation epsilon. It depends on which resonance it is that we're focusing on and how deep you are inside of the resonance and the angle of where you are around the torus. Okay, so let's look at an example of this. So these 3 different curves are for 3 different strengths of the external perturbation. And what you can see is that as you crank the perturbation up, so going from blue to orange to green, this resonance angle on the vertical axis oscillates more and more quickly. So the new time scale depends on the strength of the perturbation. So the top panel is inside one of those elliptic regions, the bottom panel is outside in the hyperbolic region. And if this plot kept going out to the right, then you would see this angle just monotonically increase or decrease. So it'd keep going, it would keep wrapping around. The upper panel, it oscillates, and in the lower panel, it just keeps going down. All right, so here's, so this panel showed us the dependence on epsilon. Now let's look at the dependence on where exactly we are inside that elliptic region. So as you move closer and closer to the elliptic fixed point inside one of those islands, you get closer and closer to this resonance angles motion being described by essentially a harmonic oscillator, but it's actually anharmonic. So as you go closer and closer to the edge of one of those elliptic islands, this oscillator gets a larger amplitude and also a longer period, just like an anharmonic oscillator does. Okay, right. So you have to know exactly the details of how you enter the resonance to be able to model the dynamics of this resonance angle. Okay, so that's the orbit. And of course, in Newtonian gravity, we don't have gravitational waves, but we're just using this as a toy model. So let's use a kludge model using some mass quadrupole and current octopole. So just the leading two parts of the gravitational wave in a kind of Newtonian description. So get the positions, velocities, accelerations, and jerks from the trajectory data that we integrated up and construct the gravitational waveform. And then so what we study is, we compute waveforms from unperturbed orbits so that we can compare them with perturbed orbits, either on a resonance or not on a resonance. And then we want to know whether or not, is the unperturbed orbit model enough? Is it good enough, or are you making a mismodeling error by not modeling the tidal perturbation? And the tools that we use for this are rather standard. So let me skip over this because I'm short on time. So just for doing the comparison, what we do is we take the frequencies from the perturbed orbits and we find an unperturbed orbit that has those same frequencies to make the comparison, as honest as possible. All right, so the punchline here is that when you're far away from resonance, this purple curve at the bottom, this is mismatch as a function of time. If you, start your model at some initial time and then integrate for a total amount of time on the horizontal axis, then what's the mismatch between the resonant and, with the unperturbed and the perturbed system? Off resonance, bottom curve, you can see that it doesn't even make it to 10 to the minus 5 mismatch. So you don't really have to worry. But the vertical axis, the green one is showing on resonance, there's a much faster increase in mismatch. And that's what we wanted to quantify. So how do we quantify it? So for a general one of these resonant orbits, there's some dephasing time. So time scale over which the match reduces by some percent. I don't remember exactly what we used, but we picked some match value. And then we found some orbit that's kind of representative at a particular value of epsilon, and then estimated the dephasing time from how long it took for the match to decrease to like 0.97 or something like that. Okay, so we did this for a bunch of different values of the tidal perturbation strength. That's the horizontal axis epsilon here. And then the vertical axis is showing what is the dephase time for that tidal perturbation. For that strength on this particular resonance. And there's a scaling here that's also kind of predicted by general principles if you open up Arnold's textbook. And we found numerically that this scaling numerically agrees with what's predicted, so that's good. So we can basically just fit a straight line on this log-log plot through these points and get an estimate of how the dephasing time depends on epsilon for this particular resonance and choice of parameters. Now, what's also plotted here for each of these horizontal curves is an estimate of the in-spiral time scale, which we haven't treated in this system at all. But what we should worry about is, if the in-spiral drives you through resonance fast enough, then these the mismatch due to not getting this perturbation right isn't really going to matter. So you want to know whether or not this dephasing time is long or short compared to the in-spiral time scale. All right, so you at every value of epsilon.
Leo, if you could wrap up in a couple of minutes, that would be good.
Okay, yeah, I think I just have like 1 or 2 more slides.
Right.
So you pick a particular value of epsilon, and as you start increasing the mass ratio Q, then your in-spiral time gets shorter and shorter, and eventually it would get down to the same level as the dephasing time. So you can determine for which mass ratios you don't need to model the tidal perturbation, and for which mass ratios you do need to model the tidal perturbation. So that basically allows you to make this plot. So that just based on this power law that we calibrated numerically, you can say that for the shaded region down here, epsilon is small enough that the in-spiral is going to be more important than the tidal perturbation. But in this region over here, epsilon is large enough that you do need to model the tidal perturbation. Okay, so of course there's a bunch of stuff that we didn't do. We just demonstrated a method for one particular perturbation. We should do everything again, but in Kerr to check that the qualitative picture is right. We should explore a bunch of different resonances. We should include radiation reaction rather than treating these as 2 independent perturbations. Okay. Yeah, so let me just wrap up because I'm over time. This was the kind of bound that you expect to see from this type of analysis, which is saying, if we think that there are going to be tidal perturbations of a particular strength around some Emery system, if it's sufficiently large compared to some quantity that you calibrate, then you should be modeling the external tides. Okay, and if you want all of the details, then check out this paper. And sorry that I ran into my question time.
That's okay. Thank you very much, Leo. If anybody has questions, please put up your hand. I can start with one. So do you have an idea of how we might go about looking for signatures of this in data, for example? People have done studies of Emery resonances, and typically you can model the transition through the resonance as well, not a jump, but a smooth change in the rate at which energy and angular momentum are being dissipated, which then turns off again.
Right. Yeah.
So modeling that kind of modifying that model.
I think that's the right picture. Of course, what a lot of people have studied is the effect at resonance of the self force as a perturbation, and so there's a certain jump in the constants and jump in the phase that's predicted across resonance for that perturbation, and presumably there would be yet another jump in the phase and the constants across resonance due to this perturbation or any other perturbation. And I don't really have an idea now of whether or not you could tease apart the effects. Like if you just see one resonance crossing, then I don't think that you have any hope of being able to distinguish how much of it was due to the self force and how much of it was due to any other effects. But presumably from the rest of the in-spiral, you have a good idea of the Emery parameters and therefore what the jump should be due to the self force. So anything that's not in agreement with that must be due to other perturbations. But again, I don't know if there's more than one perturbation, I don't know how you can tell them apart.
Yeah, I guess maybe if you measured this at multiple resonances for the same Emery, it might help. But
if we get so lucky.
Yeah. I presume we expect the 2 to 3 to be the strongest.
I think that's what Tanya and Jean-Drew Brink's paper said.
Yeah. Okay. Are there any more questions? Okay, in that case, thanks, Leo. We can move on to the final talk of the session. which is by Mickey Daisy from the University of Southampton. We'll be talking about modeling black hole binaries in the intermediate mass ratio regime.
Okay, thank you.
Minority, please. Yep, looks great. Thanks.
Okay, great. All right. Thank you, Jonathan. Yeah, so although this is a session titled EMRIs, I'll be presenting the research I've been doing during my PhD at the University of Southampton, which is actually modeling black hole binaries in the intermediate mass ratio regime. And this is done using a new model that we've developed. And this has been worked on with my supervisors, Lior Barak and Adam Pound, and also our collaborators, Harold Pfeiffer, Nicholas Vitek at the AEI, and also Hannes Rutter at the University of Coimbra. Okay, so I'll start by giving just a very brief motivation for why we need these IMRI models, and then go ahead and give an overview of our proposed world-tube excision method. I'll then give some key results from our 1+1 dimensional scalar toy model. I gave a talk at the 13th LISA Symposium, which kind of concluded here. So nice now that I'll be able to go on and show results from a 3+1 dimensional scalar toy model, and also preliminary work for the full black hole binary case. Okay, so just to remind you very quickly the motivations for why we want IMRI models, and we already heard a little bit of this from Barry. So the plot on the left is from a recent LIGO collaboration paper, the population of merging compact binaries inferred using gravitational waves through to the third observing run. So Q here is the small mass ratio, and the black contours are representing the kind of expected distribution from analysis of the second observing run. But the blue regions are representing actual observations using data from the third observing run. So we can really see now that our observations are reaching down into the smaller Q domain. And on the right, we have this familiar masses in the stellar graveyard plot. And as Barry said, we're seeing more and more disparate mass ratio binaries coming in. And in this plot, they're kind of clustered in the center there. So this really corroborates the fact that we need accurate models for IMRIs ahead of detectors such as LISA and 3G ground detectors, because these detectors will really significantly extend our observational frequency window, which will allow us to really routinely detect binaries with these smaller and smaller Qs. So let me recap the current state of gravitational wave modeling efforts with respect to mass ratio. So when you have a very extreme mass ratio, then black hole perturbation theory and gravitational self-force works very well. And then when the mass ratio is comparable, say 1 to 1 to 1 to 10, then NR is extremely successful. Although we have seen really amazing efforts from both NR and second order self-force to try and bridge this intermediate mass ratio gap. And again, from Barrow, we saw really impressive results from the second order self-force, even up to Q equals 1 in the talk prior to Leo's. But still, both these methods face challenges when moving to generic orbits in Kerr, or producing waveforms with enough orbits to constitute sufficient and accurate templates for IMRIs. So we thought, why not try and work towards a complementary model? So I'll now just explain the challenges that NR faces to push to these more disparate mass ratios, because this motivates the kind of architecture of our model. So the computational runtime in numeric relativity scales in inverse proportion to the square of the mass ratio. And so one factor of this comes from the number of orbital cycles needed to model the system. And so this is a physical feature and is always going to be the case. But the second factor comes from the number of time steps required per orbit of the model. And this is constrained by the Courant limit. And so this is a numerical feature. And the Courant limit dictates that the smallest time step in your model must be constrained by your smallest spatial step, which in turn is set by the need to resolve the smaller body, which in this case is the smaller black hole, which we call M2. So our world tube excision approach tackles this second factor. So here's a schematic of the model. So it's a synergistic model that tries to combine existing successful numerical relativity infrastructure with black hole perturbation theory. So the method introduces this region of size R around the smaller body, and this is entirely excised from the numerics. And so the idea is we're really reducing the region of space-time that needs to be highly numerically resolved. And we call this region the world tube. And within this, we use an approximate analytical solution. And this is formed from a tidally perturbed black hole metric. And so there are unknowns within the solution that can only be determined when you know the tidal environment it's within. So we determine these unknowns by matching this tidally perturbed metric to the NR solution at the boundary of the world tube at each time step of the evolution. So the idea here is that this will allow the minimal time step to grow by a factor of R over M2. So speed up factor in runtime of R over M2. And we calculated that with an optimal choice of R and a high accuracy internal solution, we could, in principle, get a speed up factor of 1 over Q with this model. So in other words, for a 1:100 mass ratio binary, in principle, we believe we might be able to get a speed up factor of 100 compared to numerical relativity alone. So we started with the scalar toy model and replaced the smaller black hole with a scalar charge, because this was really the simplest model that captured enough physics to be relevant without having to worry about the Einstein field equations and the nonlinearity, but still really test the world tube architecture. And we fixed this scalar charge on a circular equatorial orbit around a short shell black hole. So it's a very simple problem. But in this case, then we're populating the world tube with a local approximate analytical solution to the scalar wave equation. And then we performed a spherical harmonic mode decomposition to reduce this problem from 3+1 dimensions to 1+1 dimensions. And this approximate analytical solution we composed from a singular field piece and a regular field piece. And this is a kind of standard split in gravitational cell force theory. And the regular field piece contains unknown functions of time within it, which replicate the unknowns in the full gravity analytical solution, the tidal moments that I mentioned earlier. So I did have a slide that detailed the construction of this solution, but I think for the interest of time, I'm going to skip past this, and hopefully the explanation I gave was enough to summarize the idea, but we can return to it if anybody has any questions. Okay, so we devised two schemes for evolving this 1+1 dimensional scalar toy model. So we had a model that used characteristic slicing and finite difference methods to numerically evolve the field. And we had a model that used Cauchy slicing and spectral methods to evolve the field. And in both approaches, the field was evolved numerically along a time slice up to the excision region. And then field values surrounding the excision region were used to determine the unknowns in the approximate analytical solution through a particular matching procedure. So in method 1, in scheme 1, we matched these analytical and numerical solutions in open buffer regions around the world tube using a polynomial regression fit. This is kind of similar to the idea of matched asymptotic expansions in black hole perturbation theory. And in scheme 2, we saw the world tube instead as a kind of strict interface and matched for unknowns only using values of the field and its derivatives on the tube's position. And it's method 2 that we're going to pursue going forward. So I'll explain that when we go to the more complicated models. But to conclude the 1+1 case then, so I'll just show some of the key results. And again, this is scheme 1 versus scheme 2 results. And there are two main parameters of the model that we can vary to test its behavior. So we can vary the world tube radius, R, and the order of accuracy of the approximate analytical solution we use within the excision region, and we call this N. So these plots are showing the effects of both. So if you focus first just on the top two panels, there's quite a lot of information here, but on the top two panels, what's being plotted is the L1 global error for a particular model against the world tube radius for a variety of different Ns, so a variety of different orders of accuracy of the internal solution. The main takeaway here is just that if you decrease the world tube radius, you're decreasing the model error. But of course, we want to make the world tube radius as large as possible for maximum runtime savings. So you can also do this by increasing the order of accuracy of the internal analytical solution. And this decreases the error as well. The other thing to see, obviously, is that the results from scheme 2 were far superior to scheme 1, and this is just because of the accuracy of spectral methods versus finite difference methods. Scheme 2 reached errors of parts like 1 in 10 to the 12 for the smallest world tube radius that we tested. So that was really promising. And then the bottom two plots are showing the convergence of the models with the order of N, the order of the analytical solution. And overall, these convergence rates are largely consistent with what we expected from theory. So this 1+1 model really allowed us to test the behavior of the excision model and how things change when varying these key parameters. So we wrote a paper on this that was published at the end of last year, which summarizes things in a lot more detail. So I'll move on now to the 3+1 model. So it's the same physical problem, a scalar charge on a fixed circular orbit around a black hole, but we're now using the Spectre code, which is the successor of SPEC, for the numerical evolution. So we're really trialing a large amount of the infrastructure here that's going to carry over to the black hole case, because we'll be using Spectre there. So we adapt the Spectre, the domain. So the left white region is the large black hole with the standard excision inside the event horizon. And then on the right, you have the excision region around this charge Q, which we've populated again with the scalar field. This is a much more complicated numerical evolution. You have to have appropriate boundary conditions at the various junctures. So we spent a lot of time trialing those and implementing those. And another thing to note is now that the numerical evolution is in Kerr-Shield coordinates. So we want to put the approximate analytical solution into the same coordinates to facilitate the matching. So let me talk about this next. So once again, it's split into a singular piece and a regular field piece. Now, for this full scalar singular field, covariant expressions for it exist in the literature up to a particular order epsilon to the 4. And then what we did was we took these covariant expressions and we performed a coordinate re-expansion into Kerr-Shield coordinates, which requires a bit of work. It's not trivial. And then we subtracted this singular field piece from the numerical field piece, which is easy as they're both now in Kerr-Shield coordinates. And now the key idea is we choose to expand this residual field in spherical harmonics. It's written here in STF tensors, where n is a radial unit vector. This is equivalent to spherical harmonics. And the idea will be to match this residual field to the regular field piece in the interior to fit for the unknowns. So we have to also express the regular field piece as a expansion in spherical harmonics. And so we've done that here with the unknown coefficients underlined in red. So we then integrate the fields against a particular spherical harmonic conjugate to isolate a single mode, and then we can directly match the field values at the world tube boundary, which I've denoted here by gamma. And this will set the value of a particular coefficient in the regular field expansion. So the key idea is that the matching is on this mode by mode basis. And so we have some preliminary results from this 3+1 model. So we're looking at the relative error here for a couple of cases. So if we just look at the solid lines first, so this is showing the relative error for a particular model at a late time slice, which then it's settled down. The red vertical lines show where the world tube is, being plotted against the Kerr-Shield radius r. And as you go from blue to green to red, you're successively halving the world tube size, and you can see that the error is decreasing. And again, the convergence we see here is consistent with the explanations from theory. And again, it's really nice, even with this first order internal solution. So I should have specified that the solid lines are for a first order model, n equals 1, that we're seeing relative errors lower than 1 part in 10 to the 4 for a world tube radius of 0.4. And then we've just very recently repeated this with a second order model, which involved a fair bit more work. And so you can see the orange line there is the same radius as the blue line for a first order model, but second order, and you can see that the error is lower. So things are in line with expectations, but we now need to repeat the second order model for smaller and smaller r to check its convergence. And then the final steps will be to really probe the numerical savings of this excision method. This can be done by comparing the runtime of progressively smaller world tube sizes or comparing to something like a charge distribution. So I'll use my last couple of minutes to talk about the preliminaries for the actual BBH case. So these are the building blocks of the BBH gravity model. Again, we're going to be adapting the Spectre domain. So there'll be the standard excision of the larger black hole from its horizon inwards. And then there will be an excision surrounding the smaller black hole in its entirety and a portion of the surrounding space-time. Now, in this case, numerical relativity will be using the generalized harmonic gauge formalism, and the analytical solution will now be the full tidally perturbed black hole metric. So analogously to the 3+1 scalar case, we want to transform this solution into the coordinates of the numerics to facilitate the matching. However, we choose to transform to harmonic coordinates instead of generalized harmonic coordinates, as this is too challenging analytically. But this requires evolving some extra numerical infrastructure outside the tube, which I'll go on to explain. And again, then we're going to perform the matching on a mode-by-mode basis. Okay, so let's just have a little look at the analytical solution. So the tightly perturbed black hole metric, it's perturbation in this parameter epsilon, where m is the mass of the black hole and b is the characteristic length scale of the tidal field. And traditionally, these expressions exist in the literature in light cone coordinates in the Reggie-Wheeler gauge. And I'm showing you the leading piece here of the time component, and underlined again is the underlined in red again is the unknown tidal term, which needs to be matched to the exterior. So these expressions exist in the literature by Poisson and collaborators, and we want to transform these into harmonic coordinates. So these are harmonic coordinates, and what we do is we find the transformation by ensuring that they satisfy the standard box equation when they themselves are written as an expansion in terms of epsilon. So then we plug this all in and solve the box equation order by order in epsilon. So it's a bit too much to put on a slide, but so at leading order, it looks something like this. And if you do a spherical harmonic mode decomposition, you find out that at leading order, it's just Legendre's equation. And then so the solution is given by a combination of Legendre functions of the first and second kind with unknown integration coefficients. And then we impose two constraints, that it's regular at the horizon and that it contains no negative powers of m. So you're just left with this leading psi piece. And then the procedure repeats at the next order of epsilon, where the source now is non-zero, so it's a bit more complicated. And again, your solution is something with unknown coefficients depending on time and radial functions. So this repeats again at higher orders in epsilon, and then you can actually find the transformation between light cone and harmonic coordinates, and so transform the metric into harmonic coordinates. But you get these extra unknown functions of time, and that's the key idea. You have the size and also the original unknown tidal moments. So these all need to be matched for to the numerical solution. So my final slide. So the extra infrastructure I need to explain. So the numerical field is evolved in generalized harmonic coordinates, denoted here by Z alpha. And I'm using psi as a symbol for the numerical metric. And there's this gauge driver time on the right-hand side. And this is what makes it complicated to deal with the analytical solution in these coordinates. So this continues as the numerical evolution, but then we also evolve 4 scalar waves given by Y alpha, which constitute an auxiliary numerical harmonic coordinate system. And the relation between the standard harmonic with the auxiliary harmonic coordinate system and the generalized harmonic coordinate system is known. So you can actually find the numerical metric in harmonic coordinates. And then we match this numerical metric in harmonic coordinates to the analytical metric in harmonic coordinates. And again, we do this on a mode by mode basis, which produces ODEs in time for the unknowns that you saw on the last slide. And solving these can fix their values. And then the matched analytical metric should in theory provide boundary conditions for the numerical solution at the next time step, and the procedure should repeat. And all should hopefully be nice and stable. So the next steps are to really finalize the 3+1 model and test everything's in line with expectations, and then move on to numerically implement this black hole binary model. And this will actually then include the orbital evolution of the system. And when that's all said and done, then we will consider including spin and eccentricity to represent more realistic astrophysical scenarios for IMRIs. Okay, I'll stop there. Thank you. Oh, I'll get that slide.
Thank you very much, Mickey. I see Leo has a question. Please go ahead.
Yeah, nice talk, Mickey. I think that I've asked this before, but I don't remember. Do you also have a prescription for basically taking the free data, not just the Coulombic part of the field, but the propagating part of the field, and treating that analytically through the excised region?
So are you talking about the scalar models, yeah?
Well, all of them, I guess.
Okay, yeah, I think you have asked me this before, and I don't think I fully understood it before either. So yeah, we have the numerical field data propagating in the bulk outside the well tube. and then its values on the boundary alone are used to fix the analytical solution in the interior. So the field outside never propagates through, it doesn't evolve inside the well tube. Its values on each side of the well tube are only used to set the unknowns within the solution at that time step. And then I think maybe the missing link that I haven't explained is that boundary conditions are set on this numerical field at the next time step from the solution in the interior. And that's how the information feeds back into the bulk at the next time.
Right. So this analytic solution that you have on the in the interior, is it basically just assuming that the external fields at the boundaries of the region are static, or they're allowed to be?
At that time step, I suppose so. So at that time step, they're static. That's their value.
Okay, all right.
And we use this mode by mode matching or something simpler in the 1+1 case to just simply do a matching kind of Dirichlet in this case.
Yeah.
And then it's
right.
for the next time step, the boundary condition is modified so that the information flows back out into the bulk.
Right. But so, I mean, won't this mean that there will be like the excised region is effectively going to have a different set of reflection coefficients for waves that are supposed to, you know, reflect off of this spherical region of space? Because like you're handling the stationary part of the field, but not the time-dependent part of the field and in the interior.
I think I'll take a little time. Maybe I should think about that and get back to you if that's not making sense so far. The unfortunate thing is that, so I'm more based on the analytical side of the collaboration, devising the form of the analytical solutions. So my colleagues at the AEI that do the numerical implementation that handle the boundary conditions.
No, right, but even on the interior, like, it's like we're taking a low frequency limit of the boundary data, right? But only keeping the 0th order in frequency. Or is it?
Let me think about this more. I can't answer it right now. Sorry.
Okay. Yeah, maybe continue that discussion offline. We have another question from Stas. Please go ahead, Stas.
Thank you very much. It's nice to see that the scheme is actually getting realized in reality. My question is a bit outside of your main scope. It's about the second thing. You know, you have many cycles. Even if you increase the size of the secondary, you still have many cycles. Mm-hmm. However, if you look at the going to larger and larger mass ratio, it's not like you don't know where the body will be in half cycle. So your orbit is still quite close to geodesic. Can this be taken into account that you roughly know where your body will be to actually even further increase the step size in your integration? I don't know if anyone is trying to look at the problem with this point of view.
So if we know where the body would be, we can increase the step size, the time step size of the numerical evolution.
What I'm saying is that
maybe this could be incorporated if we try and push the model to further smaller Qs. I don't know if we could treat it in that kind of frame if it was something like Q1 to 100, or do you think that was possible?
Well, it's a question of how far you can make the step or approximation of your geodesic. And of course, it's getting better and better if you're going to larger mass ratio. But I'm just thinking, a bit aloud, still, that since it's not like you don't know anything where your body is going to be after some time. You do have some information. It's approximate, but nonetheless could be used. I mean, I'm not sure you will answer it now, but I'm just curious if anyone.
Well, so we have, So with the scalar case, it's fixed orbit, so that's just nice and simple. But we haven't actually implemented anything with the 2 black hole body case yet. But maybe once the initial method is actually up and running, this could be something that we could think about incorporating as a further SAVIC. I'll definitely make a note of it. This keeps going the slide on. I'm going to stop sharing.
Hey, thank you very much. I don't see any more questions.
Okay.
Mickey was the last speaker of the Emory session, and there is now a long break. Come back at 8 o'clock European time for the plenary sessions. I would encourage you also to look at the pre-recorded talks. There are several from the Emory session that are available there, so please do take a look either during the next break or at your leisure after the conference is finished. Thank you to all of our speakers and to all the people who attended, and see you in 2.5 hours.
Thanks, John. Thanks, everybody.